To understand Hardy-Weinberg equilibrium, let us examine a particular gene locus in a population of frogs that are on their way to a pond to mate. The 10 frogs shown are just a few of the many in the population. We will call this Generation 1. 70% of the alleles in the frog population are big A, and 30% are little a. In the large population, 49% of the individuals have the big A genotype, 42% are big A, and 9% are little a. The frogs shed their gametes, either eggs or sperm, into the water. Note that the frequencies of the big A and little a alleles among the gametes have not changed from what they were in Generation 1. Now assume gametes unite at random to form the next generation of individuals. The frequency of the big A allele in the tadpoles of Generation 2 will still be 70%, and the frequency of the little a allele will still be 30%. Because of the random combination of gametes, Hardy-Weinberg equilibrium specifies what the genotype frequencies in Generation 2 will be. The proportion of big A individuals in the population will be equal to the probability that 2 big A gametes have come together. This is equal to the probability of getting one gamete with a big A allele, which is 70%, times the probability of getting a second, which is also 70%. The big A genotype frequency is therefore 49%. The frequency of the heterozygote genotype is equal to the probability of a big A allele joining with a little a allele, which is 21%, plus the probability of the reverse combination, a little a allele joining with a big A allele, for a total of 42%. The frequency of the little a genotype will be 30% times 30%, which is 9%. In general, if we designate the frequency of the dominant allele as P, and the frequency of the recessive allele as Q, the genotype frequencies are P squared, 2pq, and Q squared. Allele and genotype frequencies will not change from generation to generation as long as the population is large and there is no selection.